Hello and welcome to another session in physics. In this session we'll be looking at the topic electromagnetism. But before that, let us review the previous lesson. Welcome back. Well, today we'll be looking, like I said, at the topic electromagnetism. Electromagnetism is a special kind of force field that shows the interactions between electric field and magnetic field. The principle of electromagnetism is especially important in the generation of electricity as we know it. Now, as it is with every kind of force fields, there are patterns, there are directions of field lines of force. And that is the first thing we want to look at here. We want to observe and see how patterns of a magnetic field around a current carrying conductor behaves or looks like. Now from the slide here, when a straight conductor carrying current is shown, it can be observed that it has a magnetic field around it. It is this magnetic field that helps to induce EMF and produces the required potential difference required for electrons to move from one point in a conductor to another point in a conductor. Now, when we get a current carrying conductor, let's talk about a very simple experiment. Then you get a cardboard paper. Then you have to allow a thick isolated copper wire, which is the conductor, to pass through vertically in this cardboard paper sheet. As you can see here, this is the cardboard paper. Then get a copper wire, let it pass through, two of them, let them pass through this cardboard paper as shown in the diagram here below. Now what you do next is to sprinkle some iron fillings uniformly, spread them out uniformly on the cardboard paper just around the wires that have passed through vertically. Spread them out, and then you would also connect the ends of the wire to a battery, which is what you can see here. Connect the ends of a wire to a battery, which will sort of form a short circuit since there is no external load to the system, but just connect a battery there. Then switch on the current and then place some needle compasses or some compass needle around the wire. Now notice what happens next. What happens next is that the direction of the compass swings, it changes. When you switch on the current, you notice the needles and how they point. The direction will point in either clockwise or anti-clockwise direction. You observe also that when that current is switched on, that the cardboard is gently tapped, and then the fillings on the cardboard will arrange themselves in a series of what we call concentric circles, also in either the clockwise or anti-clockwise direction. Also, as soon as the current is switched on, we'll notice that the needles will swing around and form a circle with the wire as its center. The direction of the iron fillings depend on the direction of flow of the current. So if the current is flowing in a clockwise direction, that is like this, then it means that the iron fillings will arrange themselves in this manner. But if it is flowing, the current is flowing in an anti-clockwise direction, then it means the needle fillings, iron fillings will arrange themselves in this manner as well. Now let's talk about the magnetic field around a straight conductor carrying current. Magnetic field around a straight conductor carrying current. According to this slide, you'll see that the direction and pattern of the magnetic field around a straight conductor carrying current can be determined using two rules. The first rule is Maxwell's corkscrew rule, and the second is the right hand grip rule. If you don't want to call it the right hand grip rule, you can call it the clenched fist rule. Let's talk about Maxwell's corkscrew rule first of all. Maxwell's corkscrew rule states that when a right-handed corkscrew is turned, the direction of motion of the cork represents the direction of current, while the direction of rotation of the cork represents the direction of the magnetic field. That is Maxwell's corkscrew rule. Now the second one, we have the right hand grip rule, or the clenched fist rule. This rule says that when you grip a wire with your right hand so that your thumb points in the direction of the flow of the current, your fingers will then point in the direction of the magnetic field around the wire. Remember, we said that field lines do not cut across each other, they do not intersect with each other. What that means is that while the electric field moves in a particular direction like this, the magnetic field moves in another direction, more like they are perpendicular to each other, as you can see from the slide here. At this point, let's talk about the force between two parallel current carrying conductors. There are two things we need to bear in mind. The first is that when two current carrying conductors or wires are placed parallel to each other, their magnetic fields interact. There is some sort of interaction between the two magnetic fields. The second point we want to bear in mind is that when current flows in the same direction, the conductors will repel each other, and the reverse is the case when the current flows in opposite directions, where they attract each other. So when the current flows in the same direction, they repel, and when the current flows in opposite directions, they attract each other. At this point, let's talk about the magnetic field around a circular current carrying conductor. Magnetic field around a circular current carrying conductor. Now, as you can see from this slide here, you would notice that the magnetic fields here, they are curved. Of course, lines of force are usually curved. This gives us a circular loop here. As you can see from the two lines of force, we have a circular loop. This is exactly what a magnetic field around the circular current carrying conductor. Now let's talk about the magnetic field around a solenoid. The magnetic field around a solenoid looks just like this. Now, when we talk about a solenoid, we're simply referring to copper wires that have been wound in a cylindrical format around each other, so it forms something like this. This is what a solenoid looks like. Now, Michael Faraday did a simple experiment to try to show how electromagnetism works. Michael Faraday discovered that when you bring a magnet very close to this solenoid, and then you connect a galvanometer across the two terminals, and then you bring a magnet, let's say a magnet that has a north pole and a south pole, very close to this solenoid. He noticed that when you bring this magnet very close to the solenoid, and then after some time you pull the magnet away, there is a deflection in the galvanometer. This deflection in the galvanometer simply refers to one thing, and that is that EMF is induced inside that galvanometer. So the galvanometer is a device we use to test for very small quantities of current, whereas we use the ammeter to test for big amounts of current. So the galvanometer is able to test and notice that there is an induced current here as a result of EMF that has been induced in the solenoid. Michael Faraday also discovered that the faster you repeat this process, bringing it close and then moving it very fast across the solenoid, what happens is that the magnetic lines of force are made to cut across the electric lines of force inside the solenoid here, and also the deflection is more. The deflection is huge. So either way, when you bring a magnet very close to a solenoid, if you push the magnet away from the solenoid, deflection will occur. If you push the solenoid away from the magnet, deflection also will occur. And that is what you see here as well. So it is this principle that generators in our houses use to operate. That we have inside our generators, we have a rotor and we have a stator. Rotors and stators. The stators are like the magnets themselves, and the rotors are more like the conductors that are made to rotate and cut across the magnetic lines of force, which in turn produces what we call induced EMF. So when you draw your generator and you try to use the ignition and you kick it to make the vehicle start, that is exactly what you're trying to do. You're trying to make the magnetic lines of force cut across the electric lines of force so that you can have an induced EMF and give rise to electricity. The same principle is used in the ignition system of cars, or basically anything that we can start with a key. And that is it for today's class about the magnetic field around a solenoid. Thank you so very much for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.